Dijkstra algorithm takes a graph and source node as input and returns the shortest path from the source node to any node in the graph. The return value of the algorithm is represented as a map. This map gives for every node the previous node on its shortest path. For instance, we see in blue the shortest path from the source node 1 to node 5. We get to node 5 through node 6, we get to node 6 through node 3, and finally we get to node 3 through node 1. Using this map, we can trace back the shortest path from the source node to any node in the graph. In this video, we will go through the given example to see how Dijkstra works using priority queue. And afterwards, we will see how to implement the Dijkstra algorithm. This is Khaled and welcome to Dijkstra algorithm in C++. One variant of implementing Dijkstra algorithm is to use a priority queue. An element in the queue represents a pair of distance from source to node and the node. We also need to keep track of the previous node which led to the shortest path. This will be stored inside the column through. We initialize the priority queue with source node 1 with distance of 0 and we reach it through itself. We also initialize distances to all other nodes to infinity. Next, we explore the top element of the queue, the node 1, and we remove it from the queue. Node 1 has 3 neighbors, 2, 3, and 6. Those nodes are now reachable through node 1. Since the distance to those nodes through node 1 is smaller than infinity, we update the distances to those nodes accordingly. Next, we explore the top element of the queue, the node 2, and we remove it from the queue. Node 2 has 2 unvisited neighbors, node 3 and node 4. Through node 2, we can reach node 3 with total distance of 17. 17 is larger than 9, the previous distance to node 3, hence we don't update node 3. Through node 2, we can reach node 4 with total distance of 22. 22 is smaller than infinity, hence we update node 4. Next, we explore the top element of the queue, the node 3, and we remove it from the queue. Node 3 has the unvisited neighbors 4 and 6. We don't need to check the neighbor 2 because it was already visited. Through node 3, we can reach node 6 with total distance of 11, which is less than 14, the previous distance through node 1. Hence, we update node 6. Through node 3, we can reach node 4 with total distance of 20, which is less than the previous distance of 22 through node 2. Hence, we update node 4. Next, we explore the top element of the queue, the node 6, and then we remove it from the queue. Node 6 has one unvisited neighbor, node 5. Through node 6, we can reach node 5 with a total distance of 20, which is less than infinity, hence we update node 5. Next, we explore the top element of the queue, the node 4, and then we remove it from the queue. Node 4 has only one unvisited neighbor, the node 5. Through node 4, we can reach node 5 with a total distance of 26, which is larger than the previous distance, 20, hence we keep node 5 unchanged. And finally, we explore the top element of the queue, which is the node 5, and we remove it from the queue. Node 5 has no more unvisited nodes, hence we are at the end of the algorithm. We can now use this mapping to find the shortest path to any node. Now let's have a look at one possible implementation of Dijkstra algorithm using priority queue. As we have seen, Dijkstra algorithm expects a graph as input. We will represent the graph using adjacency list. We will present the complete implementation of the graph at the end of this video, but for the purpose of Dijkstra algorithm, we need the graph to provide the following interface. GetNodes method to get access to all nodes in the graph, and getNeighborsOf, which takes a node as parameter and returns the adjacency entry of the given node. For instance, getNeighborsOf node 1 will return a vector of the nodes 2, 3, and 6, along with the corresponding distances. For now, that's all what we need to know about our graph. So let's jump to Dijkstra algorithm implementation. Here again we have the Dijkstra algorithm template function. First, we need a map to store for each node the previous node on the shortest path. Next, we need a map which store for each node the total distance from source. Then we initialize the distance from source to each node to infinity, which is some very large integer. And we set the distance from source to 0. Now we set up the priority queue. The default standard priority queue provides constant time lookup of the largest element. Since we are interested in the elements with smallest distance from source, we need to customize the standard priority queue to provide constant time lookup of the smallest element instead of the largest element. To do that, we need to provide the required comparison function. In our case, the stud greater will do the job. Our priority queue holds elements of pair of distance from source to node and the node. First, we start with adding the source node and its corresponding distance. Then we loop over our priority queue as long as it's not empty. We get the top element from the priority queue and we remove it from the queue. Next, we get the neighbor edges of the current node. Each edge has the neighbor node and the distance to it from the current node. Then we loop over all the neighbor edges. And we read the neighbor node and distance from current node to neighbor node. Then we calculate the distance from source to neighbor through the current node. Then we check if the new distance from source to neighbor is smaller than the previously calculated distance. If true, we assign the new distance from source to neighbor through the current node, and at the end, we add the neighbor to the priority queue for further processing. Finally, the algorithm returns the map previous node off. And that was the whole implementation of the Dijkstra algorithm. Before we end the video, we will present the implementation of the graph and testing code which builds a graph and called the Dijkstra algorithm. Here we have the graph API which we have to implement. First, add edge function, we assume undirected graph, hence we add the edge from node to neighbor and vice versa. Next, get nodes function. This function loops over the map and stores the nodes in a new vector and return it. Finally, get neighbors of gets as input parameter a node and returns the adjacency entry of that node, which contains the neighbor nodes along with the corresponding distances. And with the member adjacency list map, we have the full implementation of the graph class. Finally, let's have a look at some testing code. In the main function, we create the graph. We add edges, so we build the graph we see in the diagram. And finally, we call our Dijkstra algorithm function. Thanks for watching.